আচ্ছা অরিত্র স্যার, আমার কথা শুনতে পাচ্ছ?
হ্যাঁ স্যার বলুন।
হ্যাঁ বলছি অরিত্র, আমাদের ফ্যাকাল্টি গ্রুপে তুমি আরেকবার মেসেজটা দিয়ে দাও, হ্যাঁ?
আচ্ছা আচ্ছা আচ্ছা
তাহলে হয়তো অনেক স্যারেরা হয়তো এই মুহূর্তে মনে নেই, ওটা থেকে জয়েন করতে পারে।
আচ্ছা 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 ঠিক আছে। স্যার গুড ইভিনিং মনোজ স্যার।
গুড ইভিনিং। চলো কি
মনোজ স্যার গুড ইভিনিং, মৈনাক বলছি।
হ্যাঁ গুড ইভিনিং।
তাহলে কি আমরা স্যার শুরু করব মনোজ স্যার, না আর 2-3 মিনিট?
হ্যাঁ শুরু করো।
আচ্ছা
শুরু করে দাও।
ঠিক আছে তাহলে। হ্যাঁ অ্যাঙ্কারটা তাহলে একটু শুরু করে দাও, ঠিক আছে?
তোমাদের অন্য গ্রুপগুলোতে স্টুডেন্টরা জয়েন করেছে তো? মানে এখানে তো খুব কম দেখতে পাচ্ছি, না হলে যাদের জন্য প্রোগ্রাম, একটু অন্য গ্রুপগুলোতে যদি ওরা স্টুডেন্টদের ফার্স্ট ইয়ারের কোনো গ্রুপ বা কিছু থাকলে মেসেজগুলো সার্কুলেট করে নিয়ে জয়েন করে নিলে বোধহয় ভালো হতো না?
স্যার আমাদের সেকেন্ড আর থার্ড লিংকে জয়েন হয়েছে স্যার।
আচ্ছা,
কতজন হয়েছে একটু নাম্বারগুলো বলে দাও স্যার।
স্যার প্রায় 150-র কাছাকাছি জয়েন করে গেছে দুটো লিঙ্কে।
তাহলে
বা তাহলে তো খুব ঠিক আছে, ভালোই আছে, ঠিক আছে,
হ্যাঁ,
তাহলে তো শুরু করাই
তাহলে
যায়।
শুরু
শিশির কোনা
Okay,
স্টার্ট করে দে।
হ্যাঁ, স্টার্ট দেন।
Very good evening to all our respected professors and my dear friends. At first, I want to thank everyone for joining this webinar. In this wonderful evening, I feel privileged to extend my warm welcome to all present here on behalf of CARQ, which stands for Center for Astronomy Research and Quantum Computing, a multidisciplinary initiative of some enthusiastic students from our first year. I am Shishir Konasen, student of first year from the Department of Electrical Engineering.
I am Dishaponda, student of first year from the Department of Computer Science and Engineering. Now, I would like to call our respected professor, Dr. Manoj Pathak sir, to say some words. Sir, please.
Thank you. Actually, very good evening to all of you. Within a very short time, all of you of the Astronomy Research Group or Astronomy and Quantum Computation Research Group actually arranged this program. So this is very proud for us, obviously, and I hope in future we will arrange much more this type of programs to share our knowledge. Okay. So that I can remember in the last month we have set for this meeting, and in that meeting we have just decided that within a 1 month or 2 months we can arrange some programs so that all of we can listen from you. Actually, all of us are new in this field. Okay, and at the moment I have told to you that though I am a teacher of physics, but in astronomy and quantum computing I have very little knowledge. So to guide you, first thing that the most important thing is required, that I have to study along with you, and all of you take this initiative. So it is very interesting for me, and in future I hope you will be succeed, and you hope in your future all of you will be established in very good position. So regarding this, no much more time, I want to just destroy this, and you can start your program. My wish is always with you, and hope this will be successful. Thank you.
Thank you so much, sir, for inspiring and motivating us through your wonderful speech. Now, I would like to do a little housekeeping before we get started. If you have any questions during the presentation, write down your questions on the chat box. We will bring them up towards our speakers after each presentation gets over. To keep the quality of sound functional during the meeting, please mute yourself.
Sometimes physics and mathematics are mischievous in such a way that it feels too good to be true. To learn amazing things, you don't have to knock the doors of the higher science. Sometimes those beautiful results are right in front of your eyes. Now, without further ado, we call upon Shagnik Goyal from the Department of Computer Science and Engineering first year. He would present us an impressive result on the problem of collisions with a light on a new insight of collation.
Good evening to all the respected professors and the fellow students from our college. Let's play a strange sort of mathematical billiards. It's strange because here we will replace balls with blocks. We will have two sliding blocks and a wall. The first block starts by coming in at some velocity from the right, while the second one starts out stationary. Being overly idealistic physicists, let's assume that there is no friction and that all collisions are perfectly elastic, which means no energy is lost. The sharp among you might complain that such collision would make no sound, but your goal will be to count how many collisions takes place. So in slight conflict to the assumptions, a little clack sound is left to better draw your attention to that count. The simplest case is when the both blocks have the same mass. The first block hits the second, transferring all of its momentum, then the second one bounces off the wall, then it transfers all of its momentum back to the first, which then sails off towards infinity. 3 total collisions.
শাগনিক হ্যালো।
আচ্ছা বলো।
বলছি যে তোমার কি প্রেজেন্টেশনটা ওপেন করেছো এখন না করোনি? কারণ দেখা যাচ্ছে না কিছু স্ক্রিন।
অরিত্র স্যার আমরা দেখতে পাচ্ছি কিন্তু।
আচ্ছা সরি তাহলে আমারই প্লিজ কন্টিনিউ স্যার, প্লিজ কন্টিনিউ সরি।
আচ্ছা স্যার। What about if that first block has 100 times the mass of the second one? I promise I will explain all the relevant physics in due course. It's not entirely obvious how to predict the dynamics here, but in the essence of getting to the punchline, let's just watch what happens. That second one will keep bouncing back and forth between the wall and the first block with 100 times its mass, like a satisfying game of breakout, slowly and discreetly redirecting the first block's momentum to point in the opposite direction. In total, there will be 31 collisions before each block is sliding off towards infinity, never to touch again. What if the first block has 10,000 times the mass of the second one? In that case, there will be quite a few more clacks, all happening very rapidly at one point, adding up in all to 313 collisions. Hang on. Just a moment. Just a little bit. Okay, 314 collisions in total. If it was say 1 million times the mass of the second, then again with all our crazy idealistic conditions, almost all clacks happen in one big burst in time. This time, resulting in 3,141 total collisions. Now can you see the pattern here? Though it's forgivable if you don't, since it defies all expectation. When the mass of that first block is some power of 100 times the mass of the second, the number of collision we will have has the same digits as the beginning of pi. This absolutely blew my mind when I first saw it. It was originally discovered by the mathematician Gregory Galperin in 1995 and published in 2003. Part of what I think is amazing, that if ever there was any Olympic or Commonwealth Games for algorithms computing pi, this one would have to win medals for both being the most elegant and for being the most comically inefficient. I mean, think about the algorithm. Step 1, implement a physics engine. Here, Blender is used as a physics engine, but If anyone want to try, you can use other software or programs too. Step 2. Choose the number of digits d of pi. Choose the number of digits d of pi that you would like to compute. Step 3. Set the mass of one block to be 100 to the power d minus 1 and send it traveling on a frictionless surface towards a block of mass 1. And step 4. Count the number of collisions. So for example, to count only 25 digits of pi, which fits so nicely on the screen, one block would have to have 100 billion times the mass of the second, which, if that small block was 1 kilogram, means the big one has a mass equivalent to 10 to the power 8 times that of the largest supermassive black hole in the current observable universe. That means you would need to count about 31 billion clocks, and at one point in the virtual process, the frequency of clocks would be around 100 billion clocks per second. So let's just say that you would need very good numerical precision to get this thing working out accurately, and it would take a very long time to run. I will emphasize again that this process is way over idealized, quickly departing from anything that could happen in real physics. But of course, this is not interesting because of its potential as a pi computing algorithm or as a pragmatic physics demonstration. It's mind-boggling because why on earth do pi show up here? And it's such a strange way for pi to show up too. Its decimal digits are counting something, whereas usually its precise value describes something continuous. I will show you why this is true. Where there is pi, there is a hidden circle. And in this case, that hidden circle comes from the conservation of energy. In fact, there are two separate methods which are each as fabulous as the shocking fact itself. Delaying gratification though, I will make you wait until the next time to see what's going on. In the meantime, I highly encourage you to take a stab at it yourself and be social about it. It's a hard puzzle, so it never hurts to recruit other smart minds to the task. Thank you.
I would like to thank Agni for giving such a dazzling fact on this topic. So, if anyone has any questions or any doubts regarding this topic presented by Sagnik, please feel free to ask us in the chat box. I think there is no more queries from the students. Now, I would like to call our respected professor, Moinak Saha sir, to say something. Sir, please.
Okay, I was not aware that I had to share something. Okay, anyways, yesterday actually I got the information about this event, and I got the detailing of the event from a few of the organizers, and it was very well planned, and the starting of this new chapter, or whatever you call it, the association of few interested students, My best wishes are always for them. And whenever I came to know about the exact topic that they are going to deliver, the first thing that I asked them that why you are not including the senior year students. So they said that we are not that much confident to deliver it in front of our seniors. So I said that it is not a big deal to deal with a situation like that. So and even after seeing the first topic that has been covered by Sagnik Coil, and I am quite sure that you could have easily allowed our higher year students to be a part of this. They would have been enriched by this kind of webinar that has been organized by you along with the help of your faculty advisors. So nothing more to say from my side. My best wishes are always with you. I hope to see some more events like this from this particular group. Thank you. Over to Shishir Kona.
Thank you, sir, for giving us such an inspired motivational speech. Now, I would like to call our respected professor, Dr. Anirban Kundu, sir. Sir, please.
Okay, thank you. Good evening, everyone. I heard about this initiative from Auditro a few days ago, and I told him that why not? This is a very good initiative. Go for it. And today, after hearing the presentation of Sagnik, I think yes, it's worth it. Maybe as a student of mathematics, his presentation is a bit more attractive to me, but I think that the presentations yet to come will also be good and interesting. Thank you very much.
Thank you, sir.
Thank you very much, sir, for joining and motivating us. Now, I would focus on the next topic of our webinar.
Quantum mechanics, the fashion statement of science, which fascinates us a lot, but sometimes it also becomes confusing to us. Many prominent figures of 20th century could never imagine that engineers and scientists can shape and present a theoretical physics like quantum mechanics in practical platform. Even Einstein once quoted that God never pressed dice. Seems complicated, right? Don't worry. First year student Aniket Guchait, also from the Department of Computer Science and Engineering, would help to ease your complications and misunderstandings.
Good evening to all our respected professors and my dear friends. I'm Aniket Guchait from first year Computer Science and Engineering Department. Would like to present a topic named Understanding the Quantum Behavior and Introduction to Quantum Computing. So without further ado, let's start. As Disha said before, quantum mechanics, the topic of discussion of all time, sometimes seems complicated and confusing also. So we will try to understand quantum mechanical properties through a very famous example, or you can say thought experiment. So let's imagine a cat and a big box. Inside the box, a radioactive setup has been built, like you can see on your screen, such that a hammer is placed over a glass jar containing poisonous gas. When the radioactive element shows its radioactivity, the hammer will fall on the glass jar and it will break. Now let's put the cat inside the big box and sell it. Now assume we have spent 30 minutes. Now answer me a question that seems to be simple, but not really. Is the cat dead or alive? I know it's really complicated to give a defined statement at this closed box moment, because we don't even know that the hammer has fallen or not. If and only if we open the box, we will get pure state of the cat. It may be alive or it may be dead. But my question is about the complicated closed box state. How can we define the state of the cat at that moment? So our answer will be like mixed one. Some of you may say dead and rest of other may say alive, but with some confusion. I think you got my point. I'm talking about probability. This closed box state is nothing but a probabilistic state where at some instant the cat exists in alive state, also in dead state, with some certain probabilities. I'm introducing you mixed state or superposition state. Here I am representing alive state as cat alive and dead state as cat dead. So this is the mixed state which is represented by cat psi. And mathematically we can write it like this. This is nothing but the linear combination of alive state and dead state, where alpha and beta are the probability amplitudes of respective states. And this whole setup is called Schrodinger's cat experiment. Yeah, I know that only one example is not enough to understand this quantum behavior and aforesaid typical state. So for the sake of understanding it in more general way and just for continuing the fun of probability, I am giving you another example. Let's take a vibrator machine and again a box sticked with it. You all know about Luro dice. We know very well that the dice gives 6 outcomes, 1 to 6. Let's put that dice inside the box such that the upper surface of the dice will show 6. The state of the dice is represented by cat 6. Now close the box. And let's start our vibrator machine. Just like previous example, assume that we have spent 15 minutes. Now stop the vibrator machine and try to answer the same question which you are all asked in previous example. What will be the state of the dice at this closed box moment? It may be 1, 2, 3, any of these 6 outcomes. Let's see. Oh, it's 4. So the state is cat 4. Now do the same thing and spend again 15 minutes virtually. Now also if we open the box, you may get anything from the possible outcomes. The state is 2. So like previous example, the state of the dice in closed box is a probabilistic state. We can write it like this way, where alpha, beta, gamma, delta, epsilon and theta are the probability amplitudes. So we may call this is a superposition state of the dice where summation of all squares of probability amplitudes is 1. This is nothing but the total probability. I think you all are a little clear about the superposition state and a general statement that will be more cleared later on. Let's have a look on quantum mechanics. This is quantum particle. Let's say it's an electron, and I think you all have studied a little bit about Davison-Germer experiment in your plus 2 level. According to those scientists, any quantum particle like electron has a wave nature called matter wave. If you will study about matter wave, you will find that quantum particle exists in superposition state, or you can say mixed state, where any physical property like position of particle, momentum doesn't have any defined value. Rather than these physical quantities hold multiple probabilistic values at same time. And the state at which physical property of the particle holds defined value are called pure state. Let's assume for simplicity the electron has two pure states, phi dash and phi double dash. Now just try to relate with the previous examples. When we are not observing a quantum particle, the particle exists in superposition state, like the state of the cat and the dice inside the closed box in previous examples. So if we want to represent this superposition state mathematically, it will look like this. Alpha ket phi 1 phi dash plus beta ket phi double dash. This is nothing but the linear combination of phi dash and phi double dash, where alpha and beta are the probability amplitudes. Here alpha square indicates the probability of getting phi dash state, and mod beta square indicates the probability of getting phi double dash state. I said before that when we are not observing the quantum particle, it holds superposition state. But when we will try to observe the state of quantum particle, it will collapse into any of these two pure states. We may get phi dash or we may get phi double dash state. Okay. So now I think you got a general idea about the behavior of quantum particle and superposition state. Now let's know how we can do computational work using quantum mechanics principle. But at first, let's have a look on how normal computers work. To know from the basic, you should have clear idea about bit, binary digit, that is 0 and 1. Assume that the sphere is a bit and at any time it can hold 0 or it can hold 1. But a very general statement is a bit can never store two bit values at the same time. Just be patient and listen carefully. Now let's take 8 bits and assign them particular bit values like 0, 1, 0, 0, 0, 0, 0, 1. Actually, this bit code represents capital letter A, and this is 1 byte system. Now you can ask me, how do I know that this 8-bit code will represent A? So to know about this, you must have idea about ASCII code, American Standard Code of Information Interchange, and binary decimal conversion. You can see that every character has certain decimal value and it's called ASCII value. Just look at capital letter A here. Its ASCII decimal value is 65. Now you can apply decimal binary conversion to get a binary value, and it will be 1000001. You can ask me that what is the need of putting 0 bit before 1000001? As I said before, it's a 1 byte system, so there must be 8 qubits. That's why. Actually, my point is here to show you that 8 bits can hold only one possibility among 256 outcomes. What did I say? I said 8 bits can hold only one possibility among 256 outcomes. Little confusing, right? Okay, just flow with me. Our next question should be, why do we need quantum computers? Let's have a look on the power of quantum computation. As like bit, to study about quantum computation, you must have a clear-cut knowledge about quantum bit, or you can say qubit. And generally, this qubit is represented by Bloch sphere. A normal bit, like normal bit, qubit also has two pure states, 0 and 1. And the most interesting thing is, it also has a probabilistic state where it holds 0 and 1 at the same time, and that state is called superposition state, which is nothing but, again, the linear combination of 0 and 1. Just like the cat and the dice inside the closed box movement in my previous examples. When we are not observing a qubit, the qubit holds 0 and 1 values at the same time. But whenever we will try to measure and observe it, the qubit collapses into any of these two pure states. It may be 0 or it may be 1. So now let's take 8 qubits. All qubits exist in superposition state. So every qubit holds 0 and 1 value at the same time. Remember one thing, that this superposition state is probabilistic. Now just tell me how many arrangements of bit values possible for 8 qubits. As each of 8 qubits hold 2 bit values, so by using the basic concept of permutation and combination, total 2 to the power 8, that means 256 possible bit values can be stored by 8 qubits at a single time. That means at any instant, this 8 qubit system hold A, B, C, D, E, and total 256 ASCII characters. Not only capital letters, but also small letters, numbers, special characters are also contained by these 8 qubits at a single time. Where for a normal computer, a 8-bit system hold only one possibility at any moment. Can you just imagine the power of quantum computation? Let's have a look on real-time benefit of using quantum computer. Suppose Alex and Bob are two best friends. Alex has access to IBM Q, IBM's quantum computer, and Bob has Google's quantum computer and a simple desktop version. Here IBM Q and Google's quantum computer is connected through a quantum channel, and a classical channel has also been built where the desktop is connected. This is all little setup. Now Alex created an Amazon account and set 6 valued password using IBM Q quantum computer. For simplicity, let's say the password is ABCDEF. Please listen carefully. Here, for every character, 8 qubits are required. So total 6 characters means 48 qubits. And we know very well at superposition state, every qubit holds 0 and 1 values simultaneously. So total 2 to the power 48 possibilities can be held by 48 qubits at any instant until the password is sent by IBM Q to this Google's quantum computer. 2 to the power 48. If you just want to calculate, it will be 2 lakh billion possibilities at any instant where only one possibility will be correct. It's quite like the Avengers Endgame movie scene where Doctor Strange indicating Iron Man. So let's suppose a hacker is present with his MacBook and trying to hack this quantum channel. Now just think how much effort this hacker has to give to hack this password. I think you all can predict the power of quantum computation. Now you can ask me that what is the need of this classical channel, this one? Actually, Alex is sending quantum information through this quantum channel where qubits are in superposition state. So Bob needs to have a special encryption key to get the real password. So to send that encryption key, classical channel is needed. And frankly speaking, this is not the actual algorithm for quantum encryption. You need to learn source algorithm to understand how we can use quantum computation in cybersecurity field. Now let's see, other than this cybersecurity field, where we can use the power of quantum computation. Data science, artificial intelligence, blockchain and cryptocurrencies, healthcare research, finance, and again cryptography and cybersecurity, supply chain management, pharmaceutical development, fraud detection, machine learning, data analysis, and many more. Believe me, I'm not talking in the air. Google, D-Wave, Amazon Web Service, Microsoft, IBM, like big tech giants, are spending millions and billions of dollars to innovate a perfect quantum chip which can beat a supercomputer in every field. And this is called quantum supremacy. And all the companies are in this race, and our most favorite China also. The most amazing thing in this field is that the quantum computers are available on the cloud, and you can access it with some sort of with some sort of permission from the company. Google made CARQ, Python library. Microsoft introduced Q# language. IBM introduced Qiskit, Quantum Information Software Kit. And these are all open source SDK, software development kit. If you know Python, you can install it through pip installer. Okay, so this is all about my presentation. Thank you all.
I would like to thank Aniket, on behalf of everyone, for giving such an adorable insight on this topic. The chat box is open for now. If you have any questions regarding the presented topic, write down your questions in the chat box so that we are able to present your question to the speaker. I think there is no question. Now, I would like to call our respected professor, Dr. Dilip Sahu sir, to say some words. Sir, please. I think sir has some internet issues. So now lights on the next topic of our webinar. Before that, I would like to call our respected professor, Dr. Aritra Banerjee sir, to say some words.
Thank you very much. So it was a very nice presentation. Both the presentations are very beautiful, insightful, and especially quantum computation example or quantum computation as lucidly represented by Aniket. It is very praiseworthy in my opinion. So in a very short notice, what you have arranged is commendable. But as Moinak sir already pointed out, so in our future talks or in your future talks, you should also include the other students or your seniors basically. They will be immensely helped by these things because these are new topics to them. Maybe they find interest to pursue these things. So you members should also include all of our community to these things. Okay. So just like that, so it is very encouraging to see exploring these new topics aside from your everyday coursework and everything. So we are very proud of you in this sense because in a very short notice, what you are presenting is really commendable, and most of the things that Aniket already told that it was beyond me. I did not know these things basically. But as he has lucidly represented this, it ignite inspiration inside me also to understand these things. And I am sure that many of your students many of your friends who are listening to the other links, So they are also welcome. On behalf of this team, I would like to welcome them also to join this club and to explore new things beside your coursework. So we will also try to organize these things frequently, maybe once a month, twice a month, or twice in 1 month. So these things would be happening, and please include other students. Other students means your seniors in your talks after this thing. Maybe they can join the club also, and they can help you, or they can. So if many members are there, the new ideas will be floating around also. So without further ado, I would like to hand over the mic to our anchors, and for the next presentation, please, you can proceed. Thank you very much.
Thank you so much, sir. It was indeed truly inspiring and motivating for us. Now, lights on the next topic of our webinar.
Our next presentation will help us in unraveling the mysteries of the universe. Each and every entity present in the universe has been a great field of interest for each and every human being over the years. So, I would like to call upon Sorin Das from the Department of Mechanical Engineering first year to unfold the hidden mysteries of the universe that has been known to the mankind to this date.
Good evening to one and all present here. I am Sorin Das from first year Mechanical Engineering Department. Actually, I want to shed light on a very interesting topic, which is basically based upon unraveling the mysteries of universe. But to make it much more interesting, I have thought of segregating it into two parts, namely astronomy and astrophysics. So let's start. So my first topic is, what is astronomy? So basically, astronomy is the scientific study of celestial objects such as stars, planets, comets, nebula, star clusters, and galaxies, and phenomena that originate outside the Earth's atmosphere. I think the definition seemed a bit complicated. So in simple words, if I say, then it is the scientific study of all objects in intergalactic space by using observation methods. Now, many people confuse between astrology and astronomy. I must tell that both of these topics are completely different. Let me elaborate. So basically, in astronomy, astronomers and scientists try to understand the phenomena of outer space scientifically. But astrology is completely based upon belief that how will the positioning of various stars and celestial bodies affect the way events occur at Earth. So in basic terms, astronomy is completely based upon scientific observations, but astrology is based upon the beliefs that people make. Let's move on to our next topic. Here we can see our solar system. So what I have basically done here is to present a mnemonic by which we can easily remember the name of the planets. Now, I would request everyone to observe the letters very carefully, as because each and every alphabet of the very letter is written in capital. It's given as, my very educated mother just served us 9 pizzas. So it's very clear that M is capital, V is capital, and it continues so on. So basically, M stands for Mercury, V for Venus, E for Earth, M for Mars, J for Jupiter, S for Saturn, U for Uranus, N for Neptune, and P for Pluto. Well, it feels like the kids are not happy with their mom, but still no issues. Let's continue. Let's move on to the next slide. Now, this is very interesting to every one of us, the history of astronomy. So the history of astronomy dates back to the Greeks. Astronomy is basically a Greek word in which astron means star and nemein means to arrange or distribute. Early cultures such as Babylonians performed methodological observations in the night sky. They were the ones who laid the foundations for later astronomical traditions that developed many other civilizations. Especially, I would like to mention about the scientific calendars that we use today. Now let's move on to our next slide. So here I present to you amazing astronomical artifacts. So what are artifacts? So basically, artifacts are the objects which are carved by human beings and which serves as a great historical interest. And there are many such astronomical artifacts present till date. Let's see some of them. The first is Stonehenge. It was made perhaps to mark seasons like summer solstice, winter, etc. It dates back to nearly 3000 BC. Now let's move on. Here we see Sun Dagger, which is another astronomical artifact. It is basically a celestial calendar of the ancient Pueblo Indians, and it dates back to nearly 1000 AD. The picture given clearly depicts about the seasons. For example, the spring equinox, the summer solstice, the fall equinox, and the winter solstice. Now, many of you must be wondering, who are these Pueblo Indians? I must say that Pueblo Indians are not the Indian people. So basically, they are the North American habitats, right? They used to live in the North American region, especially the Spanish region. Let's move on to our next slide. Now, from here starts the main astronomy. So we are going to see about the famous astronomers who contributed to the field of astronomy. Here I present to you one of the most famous astronomers, Claudius Ptolemy. He lived around 150 AD and described the motion of planets. He published a comprehensive treatise which was known as Almagest on the movements of stars and planets. Now, before Claudius, there was this another astronomer, Hipparchus, who basically stated that Earth is placed at the center of the solar system. And it was Claudius who gave complicated geometrical concepts to prove the geocentric theory, which placed Earth at the center of the solar system. He emphasized that other planets and also Sun moved in perfect circles around the Earth. He catalogued 48 constellations, which we know till date. Let's move on to our next slide. Here is Nicholas Copernicus. On February 19th, 1473, he published that it is not the Earth, but it is the Sun, which is at the center of the solar system. And this was known as the heliocentric model of the solar system. He also discovered about the rotation of the Earth about its axis. He gave suitable explanations about the fluctuations of the Earth's seasons. I would like to ask that what is the main reason behind the fluctuations of the Earth's seasons? Don't worry, I will brief it a bit. So basically, the fluctuation of Earth's seasons occurs because of precession of Earth. And this is a new topic, a new concept, precession of Earth. So precession of Earth is basically the orientation of Earth about its axis. And it has been observed that the orientation changes over time. And this is the main reason due to which we can see the fluctuations of the Earth's seasons. I must tell you that at present, the precession of Earth is 23.5 degrees. Let's move on to our next topic. Here comes Galileo Galilei. Galileo Galilei is referred to as the father of observational astronomy. He studied speed, velocity, gravity, inertia, projectile motion, and also worked in applied science. I must say that Sir Isaac Newton proposed his 3 laws of motion based upon Galileo's discoveries. In 1610, he published a little book known as Sidereus Nuncius, where he mentioned about his observations. To be very precise, his telescopic confirmations of the phases of Venus, observation of the 4 largest satellites of Jupiter, Saturn's rings, and also analysis of sunspots. And there's a very interesting fact credited to his discovery that accidentally he converted a microscope into a telescope just by interchanging the glasses, which eventually led to the magnification of the celestial objects to nearly 30 times the initial magnification range. Let's move on to our next slide. Here is one of the most famous German astronomer, Johannes Kepler, who explained the motion of planets of our solar system. By using the voluminous and accurate information of Tycho Brahe, he was finally able to understand that the planets' orbits were ellipses but not circles, which was mentioned by Claudius. He stated his 3 laws of planetary motion, in which the first law is the law of ellipses, which states that planets move in elliptical orbits around the sun being placed at the focus of the ellipse. The second law is the law of equal areas, which states that a planet covers the same area in space in the same amount of time, no matter if it's in aphelion or perihelion. And the third law is the law of harmonies, which states that square of a planet's orbital period is proportional to the cube of the length of the semi-major axis of its orbit, or in simple terms, in mathematical interpretation, I must say that t square is directly proportional to a cube, where a is the semi-major axis of the ellipse. Let's move on to our next slide. Here we have one of the most famous astronomers, Edwin Powell Hubble. We all must have heard his name. So basically, Edwin Hubble is credited with discovering galaxies outside of our own Milky Way. In the year 1923, with his Hooker telescope, he proved to the scientific community that there was more to outer space than the Milky Way. How? Let me say it. I must say that there are about 1.5 into 10 to the power of 11 galaxies in the observable space. And Milky Way is one such galaxy. So the probability of our existence is approximately, we can assume, 1 upon 10 to the power of 11, which is infinitesimally small. So we must imagine that space is indefinite. And so is a third point, which is mentioned, that he was the first astronomer to propose the idea about the indefinite expanse of intergalactic space with a seemingly infinite amount of stars. Let's move on to our next slide. Here we have stars. So basically, stars are the brightest entity of the universe, and we all know that, right? Now, we have already seen in the previous slide that the Greek word astron means star. So let me brief a bit about stars and constellations. So a star is a sphere of gas which is held together by its own gravity. It is basically a luminous spheroid of plasma. and the closest star to Earth is our very own sun. So we have an example nearby that astronomers can study in detail. And the next closest star to Earth is Proxima Centauri, which is nearly 4.3 light years away from us. Let's move on to our next slide. Now comes stellar evolution. A star is born, lives, and dies, much like everything else in nature. Using observations of stars in all phases of their lives, astronomers have constructed a life cycle that all stars appear to go through. I must tell that the fate and life of a star depends primarily on its mass. So basically, all stars begin their lives from the collapse of a material in a giant molecular cloud, and this molecular cloud is known as the stellar cloud, from which the stellar evolution comes into existence. So the molecular cloud, or a stellar cloud as it is known as in general, is an accumulation of gas, plasma, and dust. Now, due to the presence of these components, the plasma, the dust, the gas, the movement of these components causes turbulence in the cloud, which causes knots, which then collapse under their own gravitational attraction. And this collapse causes the material at the center of knots to heat up. So that hot core is called a protostar, which eventually turns up into a star. Now it's very obvious that when we talk about stars, the other thing that comes into our mind is constellations. So let me brief it a bit. A constellation is a name given to a group of stars in the sky that make up a certain pattern. These patterns may take many forms, such as mythological creatures, animals, objects, and even people. The International Astronomical Union, also known as IAU, has recognized 88 such constellations, out of which 48 constellations were already catalogued by Claudius Ptolemy. Let's move on to our next slide. Here we see name of some few popular constellations. So the first is Ursa Major, which is also known as the Great Bear. The next is Orion, which is also known as a giant huntsman. And the next is Cassiopeia, which is known to be the Queen of Ethiopia and wife of King Cepheus, according to Greek mythology. So here we see about Ursa Major. So basically, Ursa Major is seen during summer in the early part of night. Now, if we observe the picture in the background very carefully, we can see that there are 3 stars in the handle and 4 stars in the bowl portion, which sums up to 7 prominent stars in this constellation. It has got various names in various parts of the world. So in US and Canada, it is known as the Big Dipper. In UK and Ireland, it is known as the Plough. And in India, it's our very own Saptarshi. Next comes Orion. So Orion is basically seen during winter in the late evenings from November to early May. So if anyone wants to observe the Orion constellation, they can go out and clearly observe the constellation if and only if the cloud is very clear. Now the 3 middle stars represent the belt of the hunter. Please, I would request everyone to observe the picture very carefully in the background. There are 3 middle stars which represent the belt of the hunter, and these 3 middle stars are Alninum, Mintaka, and Alnitak. It contains 2 of the 10 brightest stars in the night sky, out of which the shiniest star of the Orion constellation and the 7th brightest star in the night sky is Rigel. Let's move on to our next slide. So here is Cassiopeia. It is visible during winter in the early part of the night in the northern sky. If we observe the picture very carefully in the background, it looks like a distorted letter W or M. I must tell you that it was one of the 48 constellations listed by the 2nd century Greek astronomer Ptolemy, and it remains one of the 88 modern constellations listed by the International Astronomical Union. Let's move on to our next slide. So, the thing is that now I have mentioned about the observable parameters of space that led to astronomy. But in my subsequent presentation, I will try to explain various scientific arguments that proved these observable parameters into reality, which eventually led to astrophysics, through which we will understand that how the mysteries of the universe were finally unraveled. So, what we are going to study in a subsequent lecture is what is astrophysics, evolution of the universe, the solar system, the stars theory, size comparison of planets, meteors and comets, black hole, time travel, and extraterrestrial life. Thank you, everyone.
I would like to thank Shaurin for giving such an enlightening speech. We know that today's topic may bring up a number of questions from you, and we want to let you know that we will address as many as we can in the time we have today. So, if anyone has any questions regarding this presented topic, please feel free to ask us in the chat box.
Okay, there is a question. This is for Sagnik, I think. So Shubhradeep is asking, is there present any friction in the collision? So Sagnik may address that. We consider friction in the collision problem we already talked about. Sagnik?
Yes, sir. Can you repeat the question? I wasn't listening actually.
Means that friction has a friction is present in the problem of your collision. So consider the friction there.
No, there is no friction, and that collision is absolutely a elastic collision.
I hope Shubhradeep has already got his answer. As already, so let me explain a bit. As Sagnik has already described that it is, so this is an elastic collision. The energy has to be conserved, and friction is, all of you know, or all of you know that friction is a not conservative force or conservative drag. So it is a drag basically. So not any presence of friction was considered in Sagnik's problem. I hope you may ask any question, I must say, because and Sorin's presentation was, I must say, was also a beautiful presentation. So please over to the answers.
Sir, I have something to say to those who haven't really understood that conditions.
Okay.
In that problem, what I have discussed in my presentation, here those two blocks are absolutely, the collision is absolutely elastic, and the floor they are hitting has zero friction, and the wall they are also colliding with, that wall is something that doesn't conserve or absorb energy or momentum. So you can say that that wall has particularly like infinite mass, so it doesn't observe any mass or momentum, so that speed, momentum and energy will always be conserved, and that sound, that clack sound is only shown to count the number of collisions, not that that sound is radiating energy or something.
One question, Sagnik. Sagnik, am I audible to you?
Yes, sir.
Okay. What are the techniques by which the collision number, actually number of collision is measured? What is the technique in your discussion?
Sir, in my presentation, I have only shown the formula, but the proofs, I really wanted to show the proof in this event also, but
Okay.
I
Which
couldn't
formula actually?
because some of my slides are not ready to present here.
Okay.
It
That's okay.
involves phase space and configuration space actually.
Actually, considering energy conservation, basically, phase space. Actually, are you indicating phase space? So that would be must be energy conservation in that situation. Okay. Actually, your presentation is very good. Actually, I want to say everybody, Shorin and Aniket Guchait, you have presented very finest way. Okay.
Thank you, sir.
Okay. Okay, Shishikana, now let's start your next program.
It looks that we have covered all of your questions. I think there is no more questions from the students.
I would like to request our respected professors, if they have any questions, please ask.
Okay. Okay, then maybe so. There are not any presentations left, right?
Yes, sir.
Okay, so our beloved Dilip sir is here. So if Dilip sir is wanting to say a few words to encourage the students, it may be helpful for them. So, yeah.
First of all, I would like to thank all the organizers and speakers. They speak very nicely and explain very nicely, and we also keep up it to our good exercise. And next week, possibly, we are going to organize a webinar on astrophysics, and we Orithro and basically from basic science department, all of us, we try to organize. And after your exam will over at the end of the March, we will again organize a webinar on quantum computation, and the speaker obviously will try to join Asansol Devi College. Dr. Kaushik Mukherjee is very famous in this field, so we will try to arrange him. And in the astrophysics topics, we will try to talk. I'm already in touch with Dr. Tapos Das, the professor of Harishchandra Research Institute, and if we will get him, then it is very beneficiary for us. So again, I thank all of you.
Thank you, sir.
Thank you so much.
Yeah, this is over.
Thank you so much, sir. It was indeed truly inspiring. I think we are set for now. Thank you, everyone. And it is time to wind up our program.
Disha, before ending, I would just like to request the other students who are present, the first year students who are present here, please try to, if you are interested enough, then please try to contact with these persons. That's our proposal. So you can join and you can explore your interest through that. It is a humble request to all of you. And I am saying it again, maybe I'm repeating it, but please include the other year students also, because then it will be have more ideas and so some of the more ideas will be happening, and then it will be more successful. It will be all be beneficiary for us. And I would like to congratulate each one of you, the presenters. It was an excellent presentation, and it is a very lucid presentation. So it is for first presentation, it was remarkable in my opinion. So thank you very much for attending the talks. I would like to request all of our professors, respected professors who have attended the talk. Thank you very much. And then this I will conclude, I think. Thank you.
Thank you, sir. Thank you. And all I want to say that it was time to wind up our program. Your presence made this day amazing and interesting to us. Thank you everyone for your encouragement, due to which we were able to hold this webinar, and most importantly for giving us your precious time. Lastly, I request everyone, if we arrange any webinar in future, please join and support us. We appreciate everyone's presence. Thank you.
সৌরিন আছো নাকি? অনিকেত, সৌরিন?
Yes sir, present sir.
আচ্ছা, আমরা নেক্সট উইকে একটা অ্যাস্ট্রোফিজিক্স অ্যাস্ট্রোনমির উপরে একটা ওয়েবিনার অ্যারেঞ্জ করছি।
Sure sir.
আমাদের ডিপার্টমেন্ট থেকে অরিত্র স্যার, আমরা সবাই আছি আর কি, আমাদের বেসিক সায়েন্স ডিপার্টমেন্টের সবাই অর্গানাইজ। এবং নেক্সট
Yes,
তোমাদের এক্সাম শেষ হওয়ার পর আরেকটা করব আমরা কোয়ান্টাম কম্পিউটেশনের উপর, এবং এটাই আমরা কথা বলছি এইচআর এর। আমি বললাম যেটা তাপস কুমার দাস, খুবই ভালো নাম, শুনেছো কিনা জানি না তুমি, এইচআর এর ফ্যাকাল্টি, মানে এইচআর এর। ওনাকে যদি পেয়ে যাই আমাদের খুব ভালো, না হলে ডক্টর প্রতীক তরফদার আছে, উনিও খুব দারুণ স্পিকার অ্যাস্ট্রোফিজিক্স এর, অলরেডি ভিজিটিং ফেলো ছিল এইচআর এর, এবং এসএন বসে পিএইচডি কমপ্লিট করেছে। তো তোমাদের কিছু হেল্প লাগবে আর কি, মানে ওয়েবিনারে ফ্লায়ার তোমাদের সাথে হয়তো যোগাযোগ করবে, যদি তোমরা একটু হেল্প করো আর কি, মানে ফ্লায়ার বা গুগল ফর্মে যে সার্টিফিকেট গুলো হয়, মানে খুব আমাদেরও আর হাতে সময় নেই, 6-7 দিন সময় আছে।
হ্যাঁ আমি আছি। হ্যাঁ একটু তোরা হেল্প করো। হ্যাঁ তোমরা তো এই যে তোমাদের টেকনিক্যাল যে টিমটা আছে, এই টিমতে লিংক বানানো, এগুলো ততটা মানে ততটা তো ফ্যামিলিয়ার না, একটু হেল্প করে দিই, কারণ ওটা তোমাদের
লিংক লাগবে, তারপরে ফেসবুক ইউটিউবে সেগুলো করা হবে। এই জাস্ট তোমাদের এই টেকনিক্যাল হেল্প গুলো দরকার আর কি।
টেকনিক্যাল হেল্প দরকার, বা ধরো স্যার যেটা বললেন যে পোস্টার বা এগুলো আমাদের থেকে তোমরা অনেক ভালো করবে, মানে তোমরা যেহেতু এটা অভ্যেসে আছো, তাহলে সুন্দরভাবে ওটা একটু মানে আমি বসবো। হ্যাঁ আমরা আগে স্যারের সঙ্গে কথা বললাম, আমাদের আরেকজন স্যার আছেন অনির্বাণ, ওদের সঙ্গে কথা বলবো, তোমাদের সঙ্গে একটু কন্ট্যাক্ট করে নিই একটু এই জায়গাটাতে একটু, কারণ ওটা আলটিমেটলি তোমাদেরই, তোমরা যেহেতু এইসব জিনিসে ইন্টারেস্টেড। তাপস স্যারের তো মানে হয়তো তোমরা জানো না, উনি রিমার্কেবল, দিলীপ দা যেটা বললেন, উনি তো এই ফিল্ডের একজন মানে ভারতের মধ্যে একটা রিনাউন্ড ব্যক্তিত্ব।
হ্যাঁ হ্যাঁ, দারুণ মানুষ, যদি পেয়ে যাই, আমি অলরেডি টাচে আছি, খুবই ব্যস্ত শিডিউলে আছেন, এবং কিছু মানে ফ্যামিলিগত একটু মানে ঝামেলার মধ্যেও আছেন উনি, বিভিন্ন শরীর খারাপ, ওনার মিসেসের ক্যান্সারও ধরা পড়েছিলেন, মানে অনেক রকম ঝামেলায় আছেন উনি, জানি কিনা সময় দিতে পারবেন কিনা। তবু আমি রিকোয়েস্ট করেছি,
খুব ফরচুনেট।
হ্যাঁ হ্যাঁ,
উনি পপুলারটাও এত সুন্দর দেন, তোমরা যদি শোনো তাহলে আরো বুঝতে পারো, তোমাদের এনকারেজিং,
বিরাট ইন্টারেস্ট মানে অ্যাস্ট্রোফিজিক্স অ্যাস্ট্রোনমি।
এটাই আর ঠিক আছে। ওটা
আমরা পরীক্ষা শেষ হওয়ার পর আরেকটা করব কোয়ান্টাম কম্পিউটেশন নিয়ে, সেটা আমি, উনিও খুব ভালো বলেন আর কি, ডক্টর কৌশিক মুখার্জি।
হ্যাঁ, উনিও খুব ভালো বলেন। এবার সবাই মিলে আমরা চেষ্টা করব আরো এইভাবে
পরীক্ষা শেষ হওয়ার পরে করবো।
হ্যাঁ হ্যাঁ, ওদের তো পরীক্ষাটা এবার শুরুই হয়ে যাবে।
হ্যাঁ, এটা আমি করে নিই, নেক্সট উইক আমরা এটা করে ওটা পরীক্ষা
হ্যাঁ
শেষ হওয়ার পর ওটা অর্গানাইজ করব।
ওটা তো হবে। তোমরা মোটামুটি ওটা একটু হেল্প করো, আমাকে একটু গাইড করো। হ্যাঁ, কারণ আমরা তো অতটা জানি না এইসব টেকনিক্যাল ব্যাপার, আমাদের থেকে তোমরা অনেক বেশি ভালো জানো। সেটা জাস্ট এই বলে রাখবেন। স্যারও তো আসলে অর্গানাইজিং, আমিও আছি, স্যারও আছেন, দুজনেই আছি। তোমাদের হেল্প
ওকে স্যার,
কন্ট্যাক্ট করো, ঠিক আছে?
একদম স্যার।
হ্যাঁ ঠিক আছে স্যার। দিলীপ দা তাহলে শেষ করি নাকি আজকে?
স্যার অ্যাস্ট্রোফিজিক্সের ইভেন্টের ব্যাপারে আরেকটু বলবেন?
কোনটা কোনটা
বলো স্যার, যেটা বলছিলেন যে অ্যাস্ট্রোফিজিক্সের একটা সেমিনার হবে,
ওইটাই বলছিলেন যে তাপস আছে।
নেক্সট উইকেই হবে সম্ভবত। ডক্টর তাপস কুমার দাসের সাথে কথা হচ্ছে, তো উনি ব্যস্ত শিডিউলের মধ্যে পারবেন কিনা জানি না সময় দিতে। যদি না পায়, ডক্টর প্রতীক তরফদার আছে, উনিও খুব ভালো বক্তা আর কি অ্যাস্ট্রোফিজিক্সের ওপর পিএইচডি পোস্টডক করছে এবং কিছুদিন ভিজিটিং ফেলো ছিল HRIR হরিশচন্দ্র রিসার্চ ইনস্টিটিউটে।
খুব মানে রিনাউন্ড ইনস্টিটিউট,
নামকরা ইনস্টিটিউট, হরিশচন্দ্র রিসার্চ ইনস্টিটিউট খুব নামকরা।
দেখবে এইচআরআই এলা খুব মানে ওটা খুব টপ মোস্ট থিওরিটিক্যাল ফিজিক্স এর খুব ইম্পর্টেন্ট।
ওখানে তো আমাদের কি নাম ভুলে যাচ্ছি, অশোক সেন।
হ্যাঁ, তোমরা তো অশোক সেনের কথা তো শুনেইছো, নিশ্চয়ই শুনেছো। অশোক সেনের কদিন ফিল্ড মেডেল পেয়েছিলেন উনি।
উনি ওখানকারই
ফ্যাকাল্টি। উনি ছাড়াও অনেকে আছেন। তো যদি আমরা পেয়ে যাই ফরচুনেটলি তাহলে তো খুবই ভালো হয়, নাহলে স্যার যেটা বললেন সেটা আমরা চেষ্টা করব। ওদের কাছে টপিকটা জেনে তোমরা ফ্লায়ার মানে মোটামুটি অ্যাডভার্টাইজমেন্টের জন্য যা দরকার বা যা কিছু করার দরকার সেটা একটু হেল্প করবে, ঠিক আছে? বাকিটা আমরা করে নেব।
এবং সেটা অরিত্র শুরু করে দেওয়াই ভালো, কারণ ডেটটা টাইমিংটা বাদ দিয়ে এখন থেকেই সেটা শুরু করে দিলে ভালো হবে।
তোমরা বলো দেখি ফ্লায়ার করতে কতক্ষণ, মানে কেমন টাইম লাগে? আমার আইডিয়া নেই কি ধরনের টাইম।
আমারও আইডিয়া নেই,
ওইটার জন্যই ওদেরকে জিজ্ঞেস করছি মানে কেমন টাইম লাগে।
ফ্লায়ার বলতে স্যার
তোমরা যে একটা দিয়েছো না গ্রুপে, একটা সেই মানে গ্রাফিক ডিজাইনিং এর মতো সুন্দর দেখতে,
হ্যাঁ,
ওটা করতে কতক্ষণ লাগে, কি লাগে?
ওটা করতে অ্যাকচুয়ালি কালকে আমরা মানে এটা করেছে মেনলি সায়ন, ওই করে মানে খুব সুন্দর করে আর কি। তো 6টা থেকে বলেছিল রাত্রি 9টা এরকম 9:30 পর্যন্ত ওটা নিয়ে।
মানে একদিনে হয়ে যায় 3 ঘন্টাতে, তাই?
একদিনে হয়, হ্যাঁ, কিন্তু কন্টিনিউয়াসলি মানে বসে থাকতে হয় আর কি, মানে প্রচুর এফর্ট লাগে আর কি।
আচ্ছা ঠিক আছে, সেটা তাহলে দিদি
হ্যাঁ,
আমরা স্যার ওদের একটা টিম তৈরি করব পুরোপুরি গ্রাফিক ডিজাইন।
হ্যাঁ স্যার, আমরা টিম তৈরি করব গ্রাফিক ডিজাইনের একটা, সমস্ত ক্ষেত্রে জানা
তোমাদেরকে যেটা বলছে একটা ধরো একটা আমাদের ডিপার্টমেন্টের নাম দিয়ে প্রেজেন্টস, ঠিক আছে? মানে
তুমি একটা যারা অর্গানাইজ করেছে যেভাবে হয়, যেখানে চিফ প্যাট্রন, চিফ গেস্ট, অর্গানাইজিং সেক্রেটারি, কনভেনার সব লেখা থাকে, তো সেই একটা যদি পাও তুমি কোথা থেকে, কিংবা আমি পালেও শেয়ার করে দেবো, তাহলে ওদের সুবিধা হবে কি ফরম্যাটে করবে, মানে কোথায় কোনটা লেখা থাকে, অর্গানাইজিং সেক্রেটারি, চিফ প্যাট্রন, চিফ গেস্ট, কোথায় নামগুলো থাকে, ওটা পর একটা মানে স্টেপ বাই স্টেপ কোথায় কি লিখে।
আপনাদের সাথে স্যার একটু ডিসকাশন করতে হবে, কারণ কি ধরনের আপনি বলছেন ইলাস্ট্রেশন করতে, ওটা সেটাও ডিপেন্ড করে।
ঠিক আছে, ওটা কথা বলে নেবো। ঠিক আছে কালকে আমি তোমাদের ফোন করছি, কোথাও একটা কথা বলবো, আমাকে একটু যোগাযোগ করিয়ে দিই। মানে বেশি স্যার যেটা বলতে চাইছেন, স্যারও দেখুক, আমিও দেখছি, যদি প্যাটার্নটা পাওয়া যায় তাহলে তোমাদের একটা প্রোটোটাইপ যদি দিয়ে দেওয়া হয় তোমরা দেখে করতে হবে। তারপর জাস্ট নামগুলো বসিয়ে দিলে, টাইম বসিয়ে দিলেই তো হয়ে যাবে। মানে যদি স্কেলিটনটা তৈরি হয়ে যায়, ফরম্যাটটা তৈরি হয়ে গেলেই তো হয়ে যাবে। এটা কোনো চাপ
নেই। কয়েকটা যে টপিকসের উপর উনি বলবেন তার কয়েকটা ছবি যাতে ইন্টারেস্টিং হয় দেখতে।
হ্যাঁ, ছবিটা সেটা হয়তো
তোমরা জানো যেরকম একটা
আমি একটু গাইড করে দেবো, ঠিক আছে? কিন্তু ডিজাইনিং আমি বেসিক স্ট্রাকচারটা হয়তো কে তোমাদের বলে দেবো, কিন্তু ডিজাইনিংটা একটু হেল্প করে দেবো। আমি টাইম থাকতে বলে দেবো, ঠিক আছে? অসুবিধা ঠিক আছে তাহলে। হ্যাঁ ঠিক আছে,
থ্যাংক ইউ স্যার।
হ্যাঁ,
গুড নাইট স্যার।
Thank you, sir.
থ্যাংক ইউ স্যার, গুড নাইট স্যার।
হ্যাঁ, গুড নাইট।
এক মিনিট, হ্যালো, শোনা যাচ্ছে?
হ্যাঁ স্যার।
Yes sir.
So
Yes sir.
I must say I was very proud of you. I am very proud of you. Ekdom from the heart I am saying, because I did not expect this type of clarity in your presentations. For the first presentation, I was not able. I remembered my first presentation. It was 100% better than that. So I must congratulate all of you. তোমাদের সবাইকে congratulations, খুব খুব ভালো করেছো, খুব সুন্দরভাবে করেছো। সো কিপ ইট আপ, দ্যাট দ্য থিং, ইউ শুড নট স্টপ অ্যাবাউট দ্যাট, কিপ ইট আপ, দিস ইজ এ গুড এনকারেজমেন্ট। সো দেখো, প্রথমবারের জন্য অনেক ফ্যাকাল্টিও জয়েন করেছেন, স্টুডেন্টরাও জয়েন করেছে, হুইচ ওয়াজ নট এক্সপেক্টেড ফ্রম মাই এন্ড, but as you have presented it so lucidly and so beautifully, that ultimately it will encourage, so it will enhance the reputation of your club. And now what you have to do, you have to just officially proceed the thing and make it is official club. So you are confident enough that we can do these things now. So this is our trial thing basically. And I am already saying that, look, that question was there, Moina sir already told that please include the other student, because then it will be a uniformity. So just contact with them and something like that, more 2 or more 3 students, okay? But I must say, for the first thing, it was very beautiful. And also the anchors, I must congratulate the anchors also. They also done a beautiful job, because they are not experienced, but they have handled the situation. So it was 2 or 3 good situations also, but they have handled it very beautifully. So thank you, Savaike. Good night.
Thank you, sir. Good night, sir.
And Shorin, it was very good. Shagni, Aniket,
Thank you,
Shorin.
sir.
But Shorin, I will just give you a suggestion. Don't
Sure.
ultimately, once you are out of breath sometime, right? You are out of
Okay.
okay. So just don't. So speech should be corrected, because otherwise when
Okay.
the presentation would be long. Suppose it is 1.5 1 hours, and then the energy would be decreasing. So please keep
Yes,
in
sir.
mind. So you don't have to shout like that. Not shout. I'm not saying it in a derogatory manner. Okay. Don't you have to raise.
Yes, sir.
Now what are telling with us, or what you have now, this speech is correct. Just
Yes, sir.
normally just do the things. Otherwise it will be hectic for you if the presentation is long. Today it is not a lot of presentation, and the presentation technique, I will not. All of are beautiful, but Anike's presentation technique, the tone he has used is perfect. So that type of calmness and everything, Shagnik was very good. Shagniকের প্রবলেমটা আমি বললাম না, প্রবলেমটা খুব ইন্টারেস্টিং, এটা সবাই রিলেট করতে পারে, দ্যাট ইজ গুড। সবাই মিলে ঠিকঠাক করেছো, চলো পরের বার আবার দেখা যাবে। আর ওটা একটু যেটা দিলীপ স্যার বললো, মানে টাইমটা হয়তো অতটা নেই, আমি মানে কথা বলে তোমাকে বলে জানিয়ে দেবো, ঠিক আছে?